Welcome everyone to Algebra 2, Section 1.4, Solving Linear Systems by Graphing. And the learning target is that you guys are going to be able to solve linear systems of equations by graphing. So there's three methods to solve linear equations or linear systems of equations. And the first is graphing. We'll talk about the others in later sections. And we're also going to talk today about, well, what is a system of equations? But before we do, let's review a little bit and warm up. So, letter A, graph the line y equals 2x plus 1 on the coordinate plane below. Then complete the table. We'll do this one for that. Y equals 2x plus 1 with 5 solutions. So, first let's graph it. The m is 2 and the b is 1 because it's in y equals mx plus b form. So you begin with b on the y-axis, that's the y-intercept. Then you go with a slope of 2, aka 2 over 1, and you go up 2 and right 1, or down 2 and left 1. And from there, you extend the graph. You don't have to extend it all the way if you don't like. And draw the arrows. And I'm going to do 5 points on it. I'm going to do x equals -2, -1, 0, 1, and 2. So what are the y values at those points? You can actually just see them on the graph. When x is -2, if I got off of my graph there at the end, but if I were to continue that by counting down 2 and left 1, I would have seen that, hey, when x is -2, y is -3. When x is -1, I can see that y is -1. When x is 0, that was my y-intercept. My y value was 1. When x is 1, my y value is 3. And when x is 2, my y value is all the way up here at 5. Now for the other line, y equals -x plus 4. So the m here is -1 or -1 over 1, because that's what's with the x secretly. And the b is 4. So once again, we'll begin with b by going up 4. And since this slope is negative, it'll be going the opposite direction as the other one. So I will be going down 1 and right 1, or up 1 and left 1. And I'm just going to continue on knowing that I'm going to make a table of this one too. Oh, that line was not good. That line wasn't great, but it was slightly better. And I'm going to use this table for this equation. So y equals -x plus 4. I'm going to use the same 5 y values. And I can see same 5 x values, I should say. And then my y values at those points are as follows. 6, 5, 4, 3, and 2. Now, you might want to check with your partner, aka somebody just next to you, once they're at the same point, and say, hey, did you get the same kind of graph I did? Are is your table about the same as mine, even if maybe we don't have the same points? Those kind of things. And just check in with them real quick. When you're done checking in with them, so maybe you pause the video and you're back now, let's move on to this thinking question. Well, what do you notice about these lines being graphed above? Well, one thing you might notice is that they share a common point, or they intersect. So I'm going to write down, hey, they share a common point. You might say, hey, they intersect, so you can write that down as well. And what do we recognize from the table, specifically? Well, we recognize the common point they share is 1, 3. Oops. They share 1, 3 is the specific point that they have in common. So that leads us to this idea of a system of equations. So a system of equations is a set or collection of equations that you deal with, aka work with, all at once, at the same exact time. And so that's what we had up above. We had two equations, y equals 2x plus 1 in the blue that we did first, and y equals negative x plus 4 in the orange that we did second. And we worked with them at the same time. And that doesn't mean we graphed them at the same exact time, but we graphed them on the same graph and together. So we did one, paused, did the other. Now, systems of equations will have solutions at times. Most often they'll have solutions. And the solution is wherever they intersect. So wherever those two lines or those two equations meet. So up above, on these two lines, the solution would have been 1, 3. Because out of all the points they have individually, that's the only one that they both have, they share. And what happens algebraically or mathematically is that if you were to plug 1, 3, or if you were to plug 1 in for the x value in either equation, both equations would give you 3 as the y value. Whereas every other x value you can plug into those equations are going to give you different y values out. Meaning, hey, that's the solution. That's what works. So how do we know if we're just given a random point if that's a solution? So that's what we deal with on examples 1 and 2. We're given a system of equations which will oft be written with that symbol there, showing, hey, these go together. It's a system. And we're told, hey, is this a solution? So it's like somebody already kind of did this work, or they're just saying, hey, maybe this point's a solution. Why don't you check? It's almost like saying, hey, I wonder if this will work to solve the puzzle. So what we do is we plug in 2, negative 3 as x and y values into the equations individually. So this first equation, I'm going to replace x with 2, so negative 3 times 2, and y with negative 3, so minus 2 times negative 3. And we're going to say equals 0, because we're finishing off this first equation. Now, oftentimes, not always, I'll put like a little question mark above the equal sign saying, hey, does it equal? Because we don't know yet. That's what we're trying to figure out. You don't have to put the question mark above it. That's completely up to you. So, in order to figure out if this is a solution, we start simplifying the left side of the equation. Negative 3 times negative 2 is negative 6. Negative 2 times negative 3 is positive 6. Does 6 plus 6 equal 0? Yep, last I checked it does. So I'll put a little check mark saying, hey, that solution worked. We checked it and it worked. But that only worked for that equation. In order for it to work, it has to work for both equations, because otherwise we could say, oh, well, back on the original, negative 1, 1 works for this equation, so it must be a solution. But when we put a negative 1 in the other one, we got 5 out, so it wasn't actually a solution. So we also have to do the work of plugging 2, negative 3 into the second equation. So we get 5 times negative 2, 5 times positive 2, because that's the x value, plus negative 3 is the y, equals 6. And once again, you could put the question mark, you definitely don't have to. 5 times 2 is 10. 10 plus a negative 3, does that equal 6? It sure does not. So sometimes maybe you want to put just a slash there, maybe a little x, saying, hey, didn't work. So is 2, negative 3 a solution? No, it is not. And the reason why it was not, once again, is as we plugged it into both equations for the x and y values, one equation worked, the other one didn't. If even one of them doesn't work, or if both of them don't work, then it is not a solution. I would love for you to try example 2 on your own, so go ahead and pause the video. When you're done, continue back. So example 2 is negative 1, 2 a solution. So we're plugging in negative 1 for x and 2 for y. So negative 1 plus 6 times 2 equals 11. You can put the question mark, don't have to. 6 times 2 is 12. Negative 1 plus 12 does in fact equal 11, so that one works. The second equation, negative 2 times negative 1 for the x, minus 4 times 2 for the y. Does it equal negative 6? Negative 2 times negative 1 is positive 2. Negative 4 times 2 is negative 8. Does positive 2 minus 8 equal negative 6? You betcha. So since it works for both equations, yes, it is a solution. Once again, we did the same exact steps we did on example 1. The only difference is it worked for both equations. So now we're actually going to start solving these systems of equations, and we're going to be doing it by graphing, like I said. This is going to be the first of 3 methods we learn. When graphing, the solution to the system is the point where the 2 lines intersect, meet, touch, however you want to word it. And you can always check to make sure that it works in the original equations. Now, you don't necessarily have to. There's going to be times where let's say the homework, you might be required to, but when it's time for a test, you don't necessarily have to check your solutions, but it's something you always can do to make sure you got it right. So, in order to solve this system by graphing, we're going to graph both equations like we did in the warm-up. So let's just start doing it one at a time. So let's graph this first equation. And we're going to do this one in blue and the other equation in orange. So for the first equation, it would probably be easiest to graph it if we put it into slope-intercept form, so solving for y. So that's going to happen by moving the x to the other side. So positive 5x is going to subtract from both sides. So we'll have negative 2y equals negative 5x minus 10. Even though this is a negative 2y, you still have to subtract the 5x from both sides to move it, because the 5x is positive. Then we divide both sides of the equation by negative 2, which leaves you with y equals positive 5 over 2x, because the negative divided by negative is positive, plus 5, because negative 10 divided by negative 2 is positive 5. So the m, or the slope, is 5 over 2. The b, or the y-intercept, is 5. So I'm going to go ahead and graph that. I'm going to begin with b by going up 5. And now I'm going to use my slope. So since it's positive, it's going to look like it's going uphill a little bit. So I'm going to go down 5, 1, 2, 3, 4, 5, and left 2 to make it look like it'll go uphill. And I'm just going to keep going, so I have 3 points. I'm going to go down 5 more and left 2 more. And I'm going to connect these points. Now that I'm done with that equation, I'm going to do the other one. So I'm going to subtract 2x from both sides to start solving for y in this one as well. Negative 4y equals negative 2x plus 12. I'm going to divide both sides by negative 4. Get y equals 1/2 x as I reduce 2 and 4. And as I divide 12 and negative 4, I get negative 3. So my m here is 1/2, and my b is negative 3. So I go down 3, and I go up 1, right 2, but in this case, going this direction isn't going to help me find the intersection. So I'm going to go down 1 and left 2, the opposite direction of both, and make sure it's still going uphill. And I notice, hey, they meet, and they meet right there at negative 4, negative 5. And like I said, right now I'm not going to require on the notes that you go back and check your solution, but you're more than welcome to by plugging negative 4, negative 5 back into each original equation like we just did on the previous examples. Might also be a good idea for you to do example 4 on your own. So go ahead and pause it and then work on it. And when you're done, come back. All right, example 4, whether you were stuck or you finished, let's see how you did and let's see what to do. So I'm going to do blue and orange again. For the blue or the first equation, Once again, want to solve for y. Some of them will be solved for y already, some of them won't. And you can graph without solving for y. It's just typically easier, especially for equations like these. And we'll see why in a moment. Or actually, it would have been the same with the previous example because of the slopes being fractions. So we'll subtract 4x from both sides and get negative 3y equals negative 4x minus 3. So once again, we're moving the x to start, and we have to do the opposite. So it's a positive 4x, we'll subtract 4x. Now we'll divide both sides by negative 3, and y is equal to positive 4/3 x, which don't reduce, but the negatives make them, negative divided by negative is a positive, plus 1, because negative 3 divided by negative 3. So the m is 4/3, and the b is 1. So I'm going to graph that, beginning with b, and then going up 4 and right 3, or down 4 and left 3. Once again, it should look like it's going uphill since the slope is a positive number. And when I say uphill, I'm talking from left to right specifically. The second equation, start out by moving the x. This time we're going to add 2x because that is negative. So we'll have 3y equals positive 2x plus 9. Then I'm going to divide both sides by 3, and absolutely everything gets divided. So I get 2/3 x plus 3. So this gives me an m of 2/3 and a b of 3. So I'm going to begin with b. And I'm going to go up to right 3. Oop, I already see my intersection. That's nice. So those points intersect at 3, 5. Once again, you can check it algebraically if you want by plugging 3, 5 into both equations and making sure it works. So now I have a couple questions. Is the solution to a system of equations always going to be a single point? It's what we've seen so far, so will that always be the case? And the answer is no. And that's going to be because there's two different scenarios where it's not the case. One is parallel lines, which once again is the symbol for that. Or you can write it out as parallel. That's easier for you. As well as overlapping lines, which can be called coinciding lines, aka two lines that you graph that are really the same line. They're just on top of each other. So can a system of equation have no solution, aka they never touch, they don't share any point? And the answer is yes. That's when you have the parallel lines. They never touch, they never meet, so they have no common points, aka no solution. Does graphing always provide an exact point or solution? At the end of the day, once again, no, it doesn't. Because the parallel lines has no solution, and overlapping lines we're going to see has something else as well. So we have some system classification. So we have two broad categories. The first one is a system's either consistent or inconsistent. For a system to be consistent, it means it has at least one solution. For it to be inconsistent, it has no solutions. So if we recall, that would be the parallel lines, where they never touch. Now let's say a system does have at least one solution, so it's consistent. From there, it can either be independent or dependent. If it is independent, that means it has exactly one solution, which I'm going to shorten down to SOL there. If it's a dependent system, it has infinitely many solutions, meaning every point is shared. You might also know infinitely many solutions being called IMS for short. Now, every problem we've had so far would fall under this category of having exactly one solution, meaning those systems of linear equations would be called consistent and independent. All right, let's look at example 5. So we'll graph these as well. Thankfully, the first equation, y is already by itself, so that saves us some time here. So the m is -3 or -3/1, and the b is +1. So I'm going to go up 1 to start with my b, and then from that b, I'm going to go down 3, right 1. Because it's a negative slope, it should look like it's going downhill now, instead of uphill from left to right. My other equation, unfortunately, it's not solved for y. So I'm going to subtract 6x from both sides and get 2y equals -6x plus 8. Then divide by 2. Get y equals -3x plus 4. So this time the slope is -3/1 and the b is 4. Start with the b, begin with the b. And I'm going to go down 3 from there, right 1 from that point. And you might notice, hey, these aren't touching. And the slopes are the exact same. Meaning, hey, they're parallel lines. So the solution, there's no solution. You can write out the word solution or put SOL. And that's because, once again, they are parallel lines. So what would they be classified as? That would be inconsistent. It's inconsistent with other systems because there's no solution. Example 6. Might be a good idea to try it on your own and coming back to this video. -x plus 3y equals 6. Start by solving for y by moving the x. So I'm going to add an x and get 3y equals x plus 6. Divide by 3. Get y equals 1/3 x, because there's secretly a 1 with the x there, plus 2. So my m is 1/3, and my b is 2. So I'm going to go up 2 to start, and then from there, up 1, right 3, or down 1, left 3 to make it go uphill. And graph that there. My second equation, solve for y as well. So by subtracting 3x from each side, get -9y equals -3x plus, minus 18. Then I'm going to divide everything by -9. And get y equals positive 1/3 x plus 2. So my m is 1/3 of this line, and my b is 2 for this line. So I'm going to go up 2, and then to start, and then up 1, right 1, or down 1, left 1. And we might notice, hey, wait a second. This is the exact same line I just graphed. So this is where the lines overlap. So how many solutions are there? What's the solution? It's infinitely many solutions because they share every single point together. You can't name them all. So the classification is that first and foremost, it is consistent because there is at least one solution. And then more detail on that, and it is dependent because it is more than the one solution. It is the infinitely many solutions. So if you're ever having trouble with what these classifications are, that's completely understandable. What you can always do is just refer back to this system classification, maybe put a star by it, because we're going to be doing a lot of that. All right, so let's talk about these 3 different scenarios a little bit more when we're classifying systems. It gives a little more practice and detail with it. So there's an exactly one solution. That's what we're seeing for the majority of these examples. The solution is a single point where they touch, like right here, for example, on this graph. The system is classified, I should say, as consistent because it has at least one solution. And then specifically, it is independent because it's only one solution. And then they have different slopes, aka the lines, the equations have to have different slopes. Infinite solutions, aka these are two lines, but you really just see one because they're on top of each other. The solution is many points, specifically infinitely many points. This system is also consistent because there is at least one solution, but it is dependent because there is more than one solution. And these are the exact same equations. So not only are the slopes the same, unlike the first one we had, they are the exact same through and through. And lastly, the no solution, the pair lines that never ever touch, have no points in common, and is inconsistent because there's no solution. So you don't say dependent or independent when it's inconsistent, because that's just independent and dependent are the further describing how many of those solutions it has. We already know it's no solutions, so it's inconsistent. Things to know about parallel lines, aka the no slope ones, the no solution ones, are they have the same slope, like on IMS or infinitely many. However, they have different y-intercepts. Now I'm going to put a little thing here saying, hey, these are the classifications, and this is how you can tell them apart with the equations. Without even seeing the graph, you can tell what kind of solution you're going to get or what kind of system you're going to have as far as these classifications, just with the equation, not even looking at the graph. So I want to look back at these previous examples though, just to help us out with this. If we noticed on our no solution one, where it was inconsistent, we can see that both slopes were -3, but the y-intercepts were different. If we look at the one where it was infinitely many solutions, because they were the same line, the slopes are the same, but also the y-intercepts are the same because the equations are the exact same. So if the slopes are the same, it's either going to be IMS or no solution. So then it depends on, hey, are the y-intercepts different? And if the slopes are just different in general, then it's exactly one solution. So we're going to do what I was just talking about, where we're going to classify the solutions or classify the system just by the equation. So on letter A, we'll start with these two systems, but there's a hint. Solve for y first. I'd encourage you to work on solving for y and putting your guess as what you think the system is before continuing on with the video. Solving this first equation for y, I'm going to put an arrow to say, hey, I'm working up here. I'm going to subtract 3x from both sides and get -2y equals -3x plus 0. Don't even have to write that plus 0 though. Divide by -2. Y equals +3/2x. On to the other equation. Subtract 6x from both sides to get -4y equals -6x plus 6. Divide everything by -4. Y equals +3/2 as 6/4 reduces, times x, minus 3/2, once again as 6/2 reduces. But this time a positive and negative give us a negative. So we notice, hey, the slopes are the same, meaning it's either no solution or infinitely many solution. So then we say, okay, because they have the same slope, which one is it though? Well, we ask, are the y-intercepts different? And this y-intercept was 0, aka you don't even see it, and this y-intercept is -3/2, meaning these are the no solution ones. These are parallel lines, if you will. And you don't have to write that they're parallel lines, but it might help you to remember this. And so how would we classify it? We would say this system is inconsistent because there's no solution. On to the next system. This first equation is already solved. The second equation isn't. So we solve it, and we're going to have subtracting the 4x, which I'm going to just do my work right below, and we get y equals negative 4x plus 3, and boom, that one's already solved. Now we might already notice, hey, wait a second, these equations are the exact same. So it's the same line right here, which tells us right here from the same equation, it's the IMS, the overlapping line. So the classification is it's consistent and dependent. Last but not least, letter C. We'll have to solve both of these equations this time. The first equation, add 3x to each side to get negative 2y equals 3x plus 0, or just 3x, divided by negative 2y, and you get y equals negative 3 over 2x. The second equation, subtract 5x from both sides to get y equals negative 5x plus 6. They're both solved now, and you'll notice, hey, the slopes are different, meaning it falls under the category where there's only one solution, and so the classification is, hey, it's consistent because there's a solution, but because there's only one, we say it's independent. Now you might be wondering, Mr. Kossel, can I shorten these? Can I abbreviate them? And I would say definitely. I'm actually going to from now on. So inconsistent, you could abbreviate to incons there. Stop there if you want. Consistent, I'm okay with you abbreviating that to CONS. I'm okay with dependent being DEP. And so over here, consistent, CONS, and independent, I'm okay with IND. So you could have those written as your answers as well. Now, example 8, that one's a little bit of a bear, no pun intended, actually. But it's less of a bear once we actually have the instructions on the next page. Now, for these instructions to be useful to us, we'll want to have a graphing calculator. Now, let's say you might not have a graphing calculator at your convenience to be able to use one. Some options you have for you are you can download the app Calc84. So Calc84, which you see on my screen that I have highlighted there, it's a free app on the App Store. I believe it's on the Google Play Store as well, and it's just ad supported. So you can pay money to get rid of the apps and get a few other whistles if you want, but you definitely don't need to. So if you follow the instructions here for a separate problem that is not what this ACT question is with the bear, and we're asked to find the intersection of these functions. But we want to use a graphing calculator to use this time. That'll actually help us quite a bit. So we're going to go through some instructions on how to do that. So you have your graphing calculator, and on it you'll see at the top left of a regular handheld calculator, you'll see y equals. Otherwise, it's right here on mine. And so I hit y equals. And so you can see the locks there. Those are things that you only get if you pay for them. Otherwise, we only need the two equations for what we're going to do in this class. So there's no reason to buy the full version for the use of this class. So for the first y equals, we plug in x plus 1. Now for the x, you use the x, t, theta, n, the 0 with a line through it, that I have highlighted right here, which is directly diagonal to the second. So you really just need one of them. I accidentally hit 2, so let me delete the 1. And then I'm going to hit plus 1. So that's the first equation, y equals x plus 1. I don't have to put the y because it's already listed there. And I do the next equation, 2x plus 4. And then I hit the graph button at the top right. Let's see, both look how I want them to. And it shows me a graph. And I can see these, and I can zoom. Now be careful, when you start zooming with your hand like this, you might notice that it's getting narrower than it is, but it's not really shrinking height-wise unless I make it go height-wise. So it can be a real bother, real pain to get it to stretch proportionally. So a good way to take care of that is hitting the zoom button. So hit the zoom button, that'll take care of zooming in and out for you, and you can just drag along using your finger for it. And if you have the actual calculator, the instructions that you're given in this sheet will tell you how to zoom as well. And I'll go to those right here. So you hit the zoom button and then go through the options. You can hit zoom out, zoom out, zoom out, zoom in, zoom in, zoom in, or zoom standard, which is what I'm about to hit on my Calc 84 app, zoom standard, and that just brings me back to what it was at the beginning. On the actual calculator, you can also adjust the window you have, which is quite handy to do. We don't have that option on Calc 84 though. We won't actually need to on Calc 84. Here's the zoom out, zoom in we can do. Now, what we want to do is we want to figure out, well, where do these lines intersect? So on the TI-84, you'll hit second, calc. So second button, then the calc button at the top, and then select the intersect option. So you can type 5 to go to it, or you can move the down arrow to it and hit enter. Now, as I hit it here, it actually just, boom, highlights it for me and tells me it's -3, -2. On the actual calculator, it won't do that. It'll walk you through, hey, first curve, second curve. All it's doing is making sure, hey, first curve is on one of the lines. And then if it is, hit enter. And if you can't tell, hit the hit the left and right arrows to move the cursor so you can actually see which line it's on. Once it's on the line you want, hit enter. And then it'll say second curve. And you do the same thing and just make sure it's on the other one. If it's not on one of those, the instructions here tell you to move it up or down. And then guess. You don't actually have to guess for what we're doing here, so I wouldn't worry about it. So I just hit enter through the guess and not worry about guessing. And then it'll do the same thing mine did here, where it says, boom, there's the intersection and there's the point. So that would be your solution, -3, -2. And once again, if you have any, and on your handheld calculator, it would look like this. Now, if you're having trouble seeing the intersection, remember you're just seeing part of the graph. So just like on my app here, I'd have to zoom out to see more and more of the graph as it keeps going forever and ever and ever and ever. On the actual calculator, you have to change the window, aka what you're looking at, just like looking through a window in a house. And so what you can do is you can change the minimum x value and max x value, aka how far left and right are you seeing on this graph. So on mine, right now, I can see to the left past -70 and the right past +70. So my x min and max on my window would be -70 and +70 right now. The scale, don't really ever worry about changing those by 1. That's just saying, hey, is my graph counting by 1s or by whatever. The y min and max is how far up and down you are. So for me, I can see I'm 50 up and -50 down. So my y min and max would be -50 and +50. Once you have, the window set where you want it, hit the graph button again and you'll be good. Now let's say you don't have that available. You can just go to the website desmos.com. So to get there, just literally type in desmos.com. And right on the front page, you see this graphing calculator option. Hit that, and you start seeing these equations you can type in. So you can hit y equals if you want, or if you don't, if you just start typing like we did on the graphing calculator, x plus 1, it'll assume it's y equals x plus 1. So that would be identical to where if I just put on this one y equals x plus 1. It doesn't change a thing. And then for my other equation, I put 2x plus 1. And you can do this on a phone, on a desktop, on a laptop, whatever. And there's apps as well for Desmos on iPads and any phones. And from here, I typed in the equation wrong, 2x plus 4. The best way to see the intersection is to zoom in, and you can hit home again to hit the zoom, get it back where you want, and hit the plus button to zoom it proportionally. And if you tap on the line, you can see the intersection, and as you point at it and touch it, it says, hey, it's -3 comma -2, which is the same thing we got. Now, if a graph ends up disappearing, it's actually just because you turned off the little thing up by the equation. So you can have them on or off. So if one disappears, don't worry, just turn it back on. All right, that is example 8, but let's get to that ACT question because we don't want to forget about that. Excuse me as I take a drink of water here. So you're working hard to make some extra cash for spending money. So let's say last week you worked 14 hours at your 2 jobs combined, and you're in a total of $122 before taxes. And you have one job at Build-A-Bear that pays $10.50 an hour, and you have a job at Hy-Vee that pays $7 per hour. And we want to know, well, how many hours did you work at each job to make $122 before taxes? Hint, use your calculator to help, because like I said, this one is a bear, no pun intended. So our first step is to write a system of equations. Oftentimes in word problems, we struggle with where to start, how to get there, and whatnot. So we are going to get with a system of equations. So now we have to ask, well, what goes in the system? Well, let's underline some key information from this story problem. So, key information, you worked 14 hours. We don't really need to know that was last week. And we know we earned $122 as a total. We know Build-A-Bear pays $10.50 per hour, and we know Hy-Vee pays you $7 per hour. And we want to know how many hours did you work? So, knowing this will kind of follow the y equals mx plus b model, so we can graph it, or at least we want it to. We have to figure out what are y and x going to stand for in this scenario. So it might make sense to have x be the hours you work at a given job. Excuse me, I misspoke. We're not going to want to have just normal y and x here. Sorry about that. I misspoke. Sorry about that. Let's say we're going to do, because we can't just say total hours. I misspoke there on that and made a mistake. Because we already know the total hours is 14. What we want to know is how many for each. So those are going to be our 2 variables, what we're trying to find. So we want to know the hours at Build-A-Bear as well as the hours at Hy-Vee. So we can call the hours at Build-A-Bear, let's call that B. Okay, so hours at Build-A-Bear. And let's call H the hours at Hy-Vee. Now, let's do these equations. So you have 4 different numbers you see here in your paragraph. You see 14, $122, $7, and $10.50, which is also in dollars. So we know an equation will typically, not always, but typically have three different parts. And all of our equations so far have been something plus something equals another thing. And maybe that's been the reverse order where something's equaled two other things added together. And sometimes they've been numbers, sometimes they've been variables, sometimes they've been a number times a variable. If we look back at every single equation we've had so far, it's followed one of these models, where you have two things adding together or subtracting equaling another thing. So it's likely that we'll have the same kind of setup. But we only see four numbers here. My hint for this is to look for the labels. We see labels, we see hours as a label, we see dollars as a label, dollars as a label, and dollars as a label. Anytime you have three of the exact same label and exactly three of those labels used, those are going to go in the same equation in this scenario. So anytime you're doing a system like this and you have three of the same label and exactly three of them, they're going to go in the same system. So how we're going to do this is we're going to figure out, well, which two of those numbers are adding together and which one's the one they're adding to. Well, the one that makes sense for them to add to would be called total. So that'd be the 122. So that means we're adding 1050 or 10.5 plus 7 to get 122. Now you might be saying, well, Mr. Cosell, 10.5 and 7 don't add up to 122. That's 17.5. So what we have to do is say, well, you make 1050 for every hour you work at Build-A-Bear, so B. And you make 7 hours for every hour you work at Hy-Vee. So now if we take 10.5 times every hour you work at Build-A-Bear plus and add that to $7 for every hour you work at Hy-Vee, that's how we end up getting the $122 you made before taxes. The other equation has to involve the other number that we haven't used yet, that 14 hours. Now we have to say, is 14 going to be a total number, aka one it's adding up to, or is it one of the two numbers adding together? And it said you worked 14 hours combined at the job, so that's the amount of hours you worked total, so that's going to be what is equal. So there's no numbers left, and we're not going to reuse numbers here. What we're going to just do is do B plus H. Just the number of hours at Build-A-Bear, B, plus the number of hours at Hy-Vee, H, will equal the total number of hours, 14. So once again, that first equation has all of our dollar signs together, whereas the second equation is all in terms of hours. Now we have our system of equations. But in order to graph these, we'll want them to be in that y equals mx plus b format I was referring to earlier. So we have to get there. So let's start off by getting there by saying, let's switch x to Hy-Vee and y to Build-A-Bear. And we're just going to switch these equations real quick. So we're going to call this 10.5y plus 7x equals 122. And we could have done that from the start. I just thought it might be a little more straightforward for us to think of it as B and H for Build-A-Bear and Hy-Vee. And down here, y plus x equals 14. Now we can look at these equations and say, yeah, I can solve these for y. I can put that into y equals mx plus b form. Whereas with our other equations with b and h, it might not be as straightforward for us. So the first of these two equations is going to be more difficult than the other. So I'll start with that one though. So you would subtract 7x from both sides and get 10.5y equals negative 7x plus 122. Divide both sides by 10.5. Y equals that doesn't reduce well right now. Negative 7 over 10.5 x plus 122 divided by 10.5. We do not have to worry about reducing, thankfully, because our calculator can handle all of this. Our other equation, solving for y, is going to be a lot easier. We just have to subtract x. So y equals negative x plus 14. Now, I would recommend writing these equations down somewhere if you're going to use, like you have on your notes, but if you're going to be using them all on your phone, for example, like I am with my iPad, I have them written down elsewhere, so that way when I go to type them in, it's not going to be a pain to try and remember and switch back apps. So I'm going to go back to Calc 84. I'm going to close top right as it's playing an ad. Let me mute that. Let it go through the ad because I'm not paying for it, paying for the version because the free version works just well. Now I go to y equals again, and it has these two equations. So I hit clear and clear, or I backspace through them. Now I'm going to put in the new equations that we have. So y equals, I'm going to put it in parentheses, negative 7 divided by 10.5 x, because that's getting multiplied with x. Oops, I didn't mean to make that negative there. Let me go back and delete those. There we go. Negative 7 divided by 10.5 parenthesis x plus, this one I don't need to put in parentheses because I'm not going to multiply it with anything. You could put it in parentheses if you wanted though. 122 divided by 10.5. My other equation, a little bit simpler, negative, so I push the negative button here down at the bottom, x plus 14. Both of those equations look the way I want to right now, so I'm going to go ahead and hit graph at the top right. So here we see the graph, and I'm going to hit intersect, and it'll take me right to it. If you're not using the Calc 84 or Desmos, then you'll go through the instructions we did earlier where you hit second calc and then go to intersect, which would be under this calc option, but you don't have it here because it's already one of the options you have on this Calc 84. And it tells us the intersection is approximately 7.14, comma 6.86, just for rounding purposes. So he didn't end up working an even number of hours at each job, but the hours you worked at Hy-Vee was 7.14 hours at Hy-Vee, and you worked 6.86 hours at Build-A-Bear. So no, this problem did not work out nice and neat. Once again, a quick recap. Story problems, underlining key information helps us. From there, we had to write a system of equations, and I'm sorry I misled us at first and went down the wrong route. The route we actually needed to go was what we did, where we ended up looking at labels, and we had 3 of the exact same labels. So we put the $sign, $sign all together with the numbers, and did 10.5 for every hour at Build-A-Bear, which we called B, and then later switched to Y, plus 7 times every hour you work at Hy-Vee, which we called H, and then switched to X, equals 122 total dollars. Then the other equation was hours plus hours equals hours. So we did hours at Build-A-Bear plus hours at Hy-Vee, B plus H, equals 14, which we changed to Y plus X equals 14. From there, we solved both equations for Y so we could graph them, and when we graphed them, we found our solution.